Let us see some special type of first order reactions. Okay. First one is parallel path reactions. When we go for nuclear chemistry, we call this parallel path decay or competing reactions. Okay. Let me just give you the basic structuring. See, A gives rise to B. For this, the rate constant is K1. Similarly, A also parallelly gives C. Here the rate constant is K2. Okay. Now, for this particular reaction where A is giving both B and C in parallel paths, rate minus dA by dt can be given as, see, normally we go for K1 into A or simply K into A if this were to be a single step reaction, not a parallel one. But here, because the same A is getting converted into both B and C in a parallel path manner or the reactions, it can be written as K1 into A plus K2 into A. So K1 into A, in this case, K2 into A in this case. Okay, so that is the interesting part here. Remaining all, of course, is simple. So this can be written as K1 plus K2 into concentration of A, right? Now let us take this A here minus a dA by A. Okay, can be written as K1 plus K2 into dt, right? Up to this it is normal. Now see on integration, what do we get? Of course, the discussion will be the same as what we have seen in the first order reaction. It comes out to be minus ln A, that is equal to K1 plus K2 into T plus, of course, constant. Okay. So at a time T is equal to 0, concentration of A can be given as A naught, because we are just about to start the reaction. So amount of A or the concentration of A left can be given as the initial concentration of A, right? Now substituting this, okay, we get the constant as minus ln A naught, right? Now substituting this in this expression, we get minus ln A is equal to K1 plus K2 into T minus ln A naught, isn't it? So K1 plus K2 can be written as one by T into log A naught by A, isn't it? So this can also be written as K1 plus K2 is equal to, converting it into base 10, it can be written as 2.303 by T into log A naught by A. Check this out. So this is the rate constant expression for the parallel path reactions or competing reactions. Now, let me give you some more information pertaining to this. Now, if suppose we want to calculate the percentage yield of B, it can be given as K1 by K1 plus K2. This K1 plus K2 is nothing but K average. So K average is K1 plus K2. You can say K1 by K average into 100. Similarly, percentage yield of C can be given as K2 by K1 plus K2 into 100. Even here also, this is nothing but K average. Okay. So if you consider the concentrations of B, I mean the ratio of concentrations of B and C at a time T, that can be simply given as K1 by K2 from these two expressions. Okay. Now coming to the second type of reaction, it is a reversible reaction. Okay. Now let us take it this way. A giving rise to B, then B giving rise to A. This is KF and this is of course KB. Okay. See, in this case, let us take dx by dt. Now this is nothing but the amount that is going to react from now on. Okay. From now on, what is going to be the rate? Rate from now on depends on the amount of A left, nothing but KF into A minus X. This is the amount of A left. At the same time, minus of KB into X. Now, what amount of B is reacting from now on? A left, B reacting in the backward reaction. So in terms of A, it is A minus X, means amount of A left, KB into X, that is the amount of B formed from A, or this is nothing but A reacted or B formed, isn't it? That is now going to react in the backward reaction. Okay. So supposing if we consider equilibrium, see at equilibrium, the rate of forward reaction will be equal to the rate of backward reaction. I mean Kb into X. But the point is, it has to be taken as XE. XE even here also. That E refers to equilibrium. Okay. Now, at equilibrium, let me give it as dx by dt is equal to, of course, okay, let me do one thing. Let me give this later, but before that, let me write one more step. Now, at equilibrium, let me write dx by dt is equal to kf into a minus xe minus kb into xe. But this is equal to 0. Yeah, from this we get kf into a minus xe is equal to kb into xe, right? Now, what is kb here? Kb can be given as kf into a minus xe by xe, right? Now, let us substitute this in this expression. Okay. Then what do we get? We'll see now. Now, again, dx by dt can be written as kf into a minus x minus, of course, kb is nothing but kf into a minus xe, sorry, xe by xe. This is nothing but kb. What we have derived, we also got x, right? Now, say this can be written as kf into a minus kf into x minus kf into a into, of course, x by xe, right? Just expanding the things, plus kf into xe into x by again xe, but xe get cancelled, right? Now, the next one. So this kfx and this kfx get cancelled, right? Come on, cancel this out. So we are left with so this is kf into a minus kf into a into x by xe, right? So this is dx by dt. Now this can be written as, come on, kf into a by xe. Let us take this as common. So in the first case, it will be xe because xe and xe get cancelled and you'll be left with kf into, just for convenience sake, we are taking it that way. And the thing that is left out is x, right? Now, dx by taking this here, xe minus x is equal to kf into a by xe into dt. Now this on integration gives, okay, see on integration here we get, of course, this on integration gives minus ln xe minus x, right? So that is equal to kf into a by xe into t plus constant. Okay, see from this we can straight away write the expression for kf, just taking at a time t is equal to 0. Okay, we'll do one thing. We'll go for that. See, at a time t is equal to 0, amount reacted will be 0, isn't it? Reacted will be 0. Now, from this, constant can be written as minus ln xe. Substituting this in the previous expression, we already got minus ln xe minus x is equal to kf into a by xe into t minus ln xe. Now this is the constant. Now writing the expression for kf. Kf can be written as, now take this 1 by a into t, and of course this xe into log, this will become positive. So xe by xe minus x, right? Now converting this into base 10, that will become 2.303 by a into t into this xe into log xe by xe minus x. Okay, so this is about the reversible reaction. Problems will be, of course, little simple when compared to the derivation part. Okay. Now from this, of course, we can go for the expression for Kb also, right? Come on. Next, it's the third one. Now here, the third variety is sequential or say consecutive reaction. Consecutive or sequential. You can give them as A giving rise to B, B giving rise to C. You can just go on. The rate constants are K1 and K2. Now, this is very interesting. Come on, with respect to A, it can be given as minus dA by dt. Of course, it's directly proportional to concentration of A, or simply equal to K1 into A, right? Rate depends on the concentration of A. When you are going for rate with respect to A, then coming to this dB by dt, you know, you are getting it from A, and of course even this B also is decomposing into C. When you go for B, formed from A, then this is dissociated into C, isn't it? Or the one that is reacting. Next, coming to C, it can be written as, it is just formed from K2 into B. I mean, formed from B. It is not dissociating into anything. So let me just write it as K2 into B. Suppose you have, say, C giving rise to something like D, then it would have been minus K3 into C, right? So this is interesting. Now let us take the exponential form of minus dA by A, minus dA by dt is equal to K1 into A. This is nothing but our first order reaction, the basic expression for the first order reaction. The exponential form of this can be given as A is equal to A naught into e power minus K1 into T. You know that this is called Wilhelmy equation. Okay. Now substituting this in dB by dt expression, that is dB by dt is equal to formed from A dissociated into C. Now in this, if suppose we substitute this in place of A when this is substituted, we get dB by dt is equal to K1 into, now this A can be written as A naught into e power minus K1 into T, right? Minus K2 into B. Okay. Now this on integration gives, okay, the final expression can be written as concentration of B at any time can be given as K1 into A naught by K2 minus K1 into e power minus K1T minus e power minus K2 into T. This is what we get on integration. Okay. Now this B has to be substituted in equation dC by dt. substituting this in dc by dt is equal to K2 into concentration of B. Now this B is what we got in the previous step. Now let me substitute it in this. dc by dt is equal to, so K2 as it is, then concentration of B is written as K1 into A naught by, of course, K2 minus K1 into e power minus K1t minus e power minus K2t. This is, of course, B. Okay, so this is nothing but B. Now again, this is integrated. So this on integration finally gives us the concentration of C. That can be, of course, given as A naught by K2 minus K1 into K2 into 1 minus e power minus K1 into T into 1 minus e power minus K2 into T. Okay, or of course, some modification will give us the concentration of C as concentration of A naught into K2 by this K2 minus K1 into e power minus K1t plus K1 by it will be K2 by K2 minus 1 into e power minus K2 into T. Okay, so this is what we get on integrating the dc by dt expression. Okay, K2 by K2 minus K1, I think this is minus, no, not, no, it's not minus, into e power minus K2. Okay, this is all about the sequential or consecutive reaction.